Welcome to this episode of Robert's Creative Chronicles. Today we are going to solve this question, which states that a cantilever beam AB, this one, 2 meter long, carries a uniformly distributed load, that is a UDL, of 1.5 kilonewton per meter over a length of 1.6 meter from the free end. This is the free end. So even without you being given a diagram, you should know how to draw this diagram. This is a cantilever beam. So it carries a UDL from the free end. This is the free end. Each UDL is 1.5 kilonewton per meter over a length of 1.6. This is the length 1.6 meter from the free end. This is the free end. Draw shear force and bending moment diagrams for the beam. So let's start with the calculation. So the shear force at B, let's start. Shear force at B is 0 because the shear force here, when this UDL, when you calculate the total UDL, it will be acting at the center of this length, 1.6 meter. It will be acting at 0.8 meter. So the shear force will be acting at the center here of this length. So there will be no force here. So since the shear force is acting, this UDL, when you multiply, it will be acting at the center. When you multiply this UDL by the total length, the magnitude will be acting at the center here. There's no force here. There's no point load here. So there's no weight acting here. So here, hence, is 0. So let's move to the next point, FC. FC. Now, when we find the total point load, when we convert this UDL to point load, that is by multiplying this by this, to be 1.5 times 1.6. So this 2.4 kilonewton is acting at the center, that is 0.8 here, of this 1.6 here, somewhere here. So, and that weight will also be the total weight here, because as I said in my last video, all the total weight here, the magnitude is felt at this point. So this point, any weight here, the total weight before this point is the weight here, is the shear force here. So all the forces, all the point loads, or the UDL that you add here before this point here, all the ones that are before here when you are going like this, before this point, the magnitude will be acting here. So that means the total load here is 2.4 from the calculation. That means the shear force here at this point is also 2.4 negative. This is acting downward, negative 2.4 kilonewton. Which is 1.6 times 1.5. Then my FA is also negative 2.4 kilonewton. So this in bracket, let me write 1.6 times 1.5. How you know? So this is the total weight, total UDL. Hence, now let's move to the bending moment calculation. This is the shear force calculation. Let me write it. Shear force. Now the bending moment. Now the bending moment at P is 0. It's negative Wx, which is, there's no force here at this point acting here. So W is 0, the distance also 0, so everything here is 0. So the bending moment at C is what? There will be a force, a point load acting at the center here. So that point load is what? Is 2.4 multiplied by the distance from here to here is what? Is 1.6 divided by 2. So which is what? 2.4 times 1.6 over 2. 1.92. 1.92 kilonewton meter. Yes. So the answer is 1.92 kilonewton. The bending moment at C is 1.92 kilonewton because there will be a force, a point load acting at the center. We converted this UDL to a point load acting at the center at 0.8 here. So the weight, the point load multiplied by the perpendicular distance from this C. The distance from C to that center is 0.8. That's 1.6 over 2. So if I multiply it, my bending moment at C is this. So then finally, our bending moment at A is what? At A will be this point load, the point load I got from converting this UDL by multiplying it by the distance occupies. So I multiplied it by the distance. So from here to here is 1.6 over 2, which is 0.8. Then from here to here is what? 2 minus 1.6. Here to here is 0.4. So it's 0.4 plus 0.8. So I will say it is 1.5, no, sorry, 2.4 multiplied by what? 0.4 plus 0.8. So you put this in a calculator, 2.4 divided by 0.4 plus 0.8 is 2.88. So you see 2.88, 2.88 kilonewton meter. So the bending moment at A is 2.88 kilonewton meter. So now we can move to the diagram drawing. So when drawing the diagram, you first project these points down. Any number of points they give you, you project all of them down. So then you draw a horizontal line, any point. Next, so you start. In this one, there's no point load. It's a UDL, uniformly distributed load. So from this point, this UDL at the shear force now at point B is 0. So D is 0. So now the shear force at point C is what? At B is 0. So at C is what? Negative 2.4 kilonewton. So at this point is negative 2.4 kilonewton. So you can take any scale in this one, or you can do a sketch. I'll do a sketch now in this one. I'll not take any measurement, any scale, but you can do a scale. You can say, as I did in my last video, I'll drop the link of that video under the description, so if you have any problem, you can refer to it. So, but in the last one, I used the scale, equal scale. I said 1 kilonewton to 1 centimeter. 1 kilonewton to 1 centimeter. That's the one I used. But in this one, I'm not using a scale. A sketch is also correct. When you are using a graph, you can use a scale. But this one, I'll just assume, maybe I'll say 2.4. Let's say 2.4 kilonewton. In the last one, I used a scale. I actually measured 2.4. But this one, I'll just come here. Maybe this point, I'll say here. This is a sketch, not measured. So this is my 2.4 kilonewton. At C, FC is 2.4. So at C, this is your A, C, and B. So at B is 0. At C is 2.4. Here also is 2.4. So 2.4. So when you know that from B to C there's a UDL. So you take a straight line curve, join it. Then here there's no road. There's no road here. So you just continue it constant like this, and then you close the curve. So from here to here is 2.4. So it's representing 2.4 kilonewton. So this is the distance. So this is my shear force diagram. Shear force diagram. So this is the shear force diagram. Anywhere you see this point road, you represent a straight line. A straight line curve like this, a slanting curve. So if it were a point road, you go down to represent the shear force, like I did in that last video. The link is in the description below. You can go and check it. So that one, it was a point road I solved. I went so the graph of drawing a point road is different from that of drawing a UDL. So that's all you need to know. So let's move to the bending moment. So the bending moment, you draw in the same way. You draw a straight line, a horizontal straight line. Then the bending moment at B, this here is A, C, B. The bending moment at B is 0. So in the same way, mark 0 there. So I am assuming that this is my origin. Every horizontal line I'm drawing, I am assuming that this is my origin line. The axis that, like the x-axis that passes through the origin. So downward is negative, upward is positive. There are some graphs that actually they draw it at the up portion of this line. So that one, they're using a convention that is different from this one. But any one is correct. All of them are correct. This one, any force acting downward, I take it as negative. Anyone acting upward is positive. So when we're going to do a simply supported beams, that those ones, the forces are going upward, so we'll take it as positive. No, but this one, they are coming down, so I'm using the lower part of the axis of the graph, the Cartesian graph. So now I've marked this point, yes. So at C is 1.92. Bending moment is 1.92. So at C, you come, maybe this is my 1.92. Then at A is 2.88. Or you can actually measure it using scale, but and this I'm doing a sketch. 2.8, all of them are correct. And this is 2. Let me assume this is my 2.88. So then now for bending moment, the UDL is represented by a curve, a parabolic curve. That is why I'll take this, my French curve, and draw a parabolic curve. From here, B to C. Yes. Then this one, there's no road there, so you just join it with the horizontal straight line. Okay, but it's to this point, so you join with the normal straight line curve, not horizontal line, straight line curve. Is this one I'm using horizontal line? This one is a straight line curve since bending moment. But where there is UDL, you use a curve, parabolic curve. But where there is no UDL, you use this one right here, you use a straight line curve. So this is my bending moment diagram. So this is the bending moment diagram. Here is the distance, that which represents the bending moment, which is 2.88 kilonewton meter, and this is at C 1.92. So note this is negative and this is also negative. I think I forgot to put that at the beginning of when I was solving it, but they are both negative since the forces are or the point loads, since the point loads or the UDL are acting downward. So, and here is the shear force diagram and the bending moment diagram. So I hope you understood this episode. If you have any question, feel free to contact me using my WhatsApp or email written in the description below, or you can write them in the comment section. Thank you for watching. Please don't forget to like, share, and subscribe to my channel, and hit the notification bell to get notified as soon as I drop a new video. Thanks.